online for you guys. All right, so let's start with reviewing. We're going to review electron configurations, the rules, hybridization, and Lewis structures with maybe a little bit with geometry that goes with it. Okay, so as far as the electron configuration goes, kind of the basics, you guys seem like you remember, but we just wanted to know what each of the rules were. So the first one, these are in no particular order, but at Pauli exclusion principle. Exclusion. Yep. That's not the order that goes. No, I appreciate it. No, I appreciate it. It's been a long day, but you know, it's fine. So Pauli exclusion, that's an L. And so this is the idea that every orbital, and remember that when we do our electron configurations, each orbital can hold 2 electrons. And the reason it can hold 2 electrons is because those electrons can travel in different paths within there. So they're not going to overlap. So Pauli exclusion principle is the one that tells us that. So each orbital holds 2.
And they have, is it kind of saying the same, they have to have like different storms?
Mm-hmm. Yes, and so the kind of fancy terminology that goes with this is each electron has different spins to minimize repulsions. So I'd say different spins. I think the biggest thing that's hard about the periodicity unit is understanding the terminology behind it, because AP is going to use the fancy terms and they expect you to use the fancy terms. So you want to be careful, especially trends. I know you guys didn't say really that's necessarily something you wanted to talk about for today, but the trends, you just want to be really careful. It's not enough to say, oh, it's on the periodic table, so that's why it's bigger. Well, that's not even close to right. So the periodic table is a good way for you to remember it, and so you can kind of clue it in. But when you're giving reasons, try to use words that would kind of go in this. It has to do with your repulsions or smallest energy or configuration, that kind of thing. So, Pauli exclusion principle. That's maybe all I would say about that one. Do you guys have questions on it? Okay, so then we have Hund's law. Like I said, no particular order, just the ones I think of. And this is the one that we call the empty bus seat rule. Don't put that on the AP test. Well, what's going on with my marker? So each electron is going to get its own location prior to sharing any locations. So that's where you have, like in the P level, you have 3 different orientations for your possible orbitals. And so you'd put an electron in each before you go back and you would add any second electrons within there. So Hund's law just gives us that idea that electrons are going to provide their own space, once again, to minimize repulsions, because if electrons are kept in separate locations, that's going to be less energy. That's going to be the lowest energy configuration, because you're minimizing the repulsions between your electrons. Like, that's the kind of terminology you'd want to use with that. And so remember that each of these have equal energy, so it doesn't matter which one it would go into. But if you only have one there, that's easier. It's less energy for the atom. So far, so good. And then the last one is Aufbau. And Aufbau's principle, he said they're going to fill the lowest energy first. And so you've got 1s, 2s, 3s, 2p, 3p, 3d, 4s, 4p, so on and so forth. So that's why you would do 1s, and then 1s, and then you'd fill 2s, then you'd fill 2p, then you'd fill 3s, then you'd fill 3p. We're going to go to 4s first before we go down to 3d, because this comes first and this comes second because of Aufbau's principle. This is a smaller orbital. It requires less energy for the atom to create or open up the s orbital. So it can hold those 2 electrons before it will open the 3d orbital. The 3d orbital is closer to the nucleus, but it's larger in size. So you kind of have to balance those two things.
But for like a Ti+2 ion, you would get rid of the 4s, so it'd just be 3p3d.
Right. Right.
So the difference between orbitals versus like shells. Orbitals are like the S's and P's and D's, and they tell how many electrons they can hold, or like how many electrons they can hold, versus like the shells are like 1, 2.
Yeah.
3.
So this would be an energy level, an energy level, an energy level. So the 1s, the 2s, those are your energy levels. And then the S's, the P's, those are your orbitals.
So energy levels come like first when like ions, like when they use electrons, they would always take them from the like outermost energy level.
Correct.
Not like the outermost level.
If we're going to make an ion, you're going to go to the highest energy level and pull those electrons from there.
That's
And-
what I'm saying.
Exactly. And so keep in mind that what's happening is those guys are the furthest from the nucleus, so they have the least attraction. So it requires the least amount of energy to actually remove those electrons. So that's kind of a different but similar reasoning behind that. Okay. Other questions about that? Have you guys watched videos online? Can you hear the people that are talking out there? Sometimes. I don't know if I should be restating questions. Okay, so then we're going to, so we kind of talked about transition cations. Did I take care of that, or do you want to talk about that more? Good.
Trends?
Transition cations.
Oh,
Sorry. No, I can't speak. I apologize.
Yeah.
And we did rules, so I'm going to say moving on to hybridization. Okay. Okay. Okay, so hybridization, there's kind of two ways to think about it. It's a huge, gigantic concept that we're going to pare down to a simple way to memorize it. Is that even in here? Mhm.
I didn't see it.
I wouldn't be surprised if it's not in here.
I don't even know if it's in the video.
It's probably in the bonding section. Yeah, it's on page 166.
Can we write in this book?
I mean, I prefer you not, but.
Just wondering if there's clues.
So when our orbitals combine to create a new hybrid orbital. So what we're getting at here on this one, like carbon here is going to go and it's going to bond to hydrogen. Like that. I guess we're going to go kind of backwards if we do Lewis structures and then come back to hybridization.
So
Hmm?
it's like a bond.
Right. Yes, that's very true. So carbon there, carbon's configuration, you've got 1s2, 2s2, 2p4, right? 2p2. Carbon have 6? Jokes. I am. Because then it has to have 4 valence electrons. Ooh, sorry, guys. Okay, so this one's not involved in our bonding because that's a filled lower level electron. But that means my bonding electrons are here in 2s2 and 2p2. And we just talked a second ago about how those orbitals don't have the same amount of energy. So when we start adding electrons to it, which electron gets to go to the lower energy one gets to go. Electrons don't have feelings. But the idea being that isn't equal energy, right? So what the atom does to balance its energy is it hybridizes the orbitals. And it actually literally combines the s orbital and the p orbitals together to make a brand new orbital that has the same amount of energy. So it has 4 new locations to put electrons. And so carbon takes this s orbital And then remember, you've got these p orbitals that kind of look like that, and smushes these each together to create a brand new orbital. And so carbon has kind of like, imagine, I don't know, we're just imagining it looks like this. And then it's got a second orbital. That's terrible drawing. I'm sorry, I have no ability as art skills. Don't tell Miss Stelter. Okay, so just imagine we've got carbon's kind of nucleus here in the middle. You get the point. And so now we've got these equal places, and each one has an electron available, ready to be bonded with. And so they put their electrons kind of out amongst themselves. And so that's where those hydrogens come into play. They also have an electron, and so they're going to overlap with that orbital. So here's my hydrogen, and this is representing my carbon. And so now the hydrogens have a place to come in and bond, and they're going to overlap with the orbitals. And now they can share their electrons, and each electron's sharing in a location that has the same amount of energy because of this hybridization that's going on there in the center. So that's like what hybridization is.
How would you write that?
And so the way you figure out how it's hybridized is going to be based on how many electron domains you have. So remember, electron domains are just anywhere you have electrons. And so this is seen as either a lone pair or a bonding pair. And so here I've got a bond, 2, 3, 4 different bonds. So that means I have 4 electron domains. So when you're going to hybridize, you have to remember your order of your electrons. So, or your order of your orbitals. So you've got 1 s orbital, you have 3 p orbitals, and you have 5 d orbitals. And so you're going to go down the list, essentially s, p, 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 d. And you're just going to count them, right? So I have 4 electron domains, which means I'm going to use 1 s and 3 p's. So when I say what my hybridization is, I would be, it's not an s.
There.
Yes. I don't know why my brain is just like, I can't say that and write it at the same time. Okay, sorry. sp3 hybridized, sp3 hybridized? Does it go
Yeah, it goes like that.
on the top or on the bottom? I think it goes on the bottom. I'm having a moment. I'm having a moment, guys.
On the top.
It's in the bottom.
I think mine is on the top.
Uh-oh. I thought it was a subscript.
I think it's a subscript, but I don't know why my brain is just
It's a
struggling with that.
superscript in the bottom,
Okay.
but I'm not doing it. Does it matter?
What's up?
We're doing an AP review. I'm being recorded. Just heads up. You guys want to say hi to Mr. White? Do you want me to come back and find you later?
No.
Swathe is going to leave 30 seconds ago, and everybody else is going to leave probably shortly after that. Yeah, it's a superscript. My brain just was having
Does it
struggles.
matter then?
No, I mean, it's.
Can it be a subscript or just
I don't think that they're going to take points off because you put the 3 small instead of big. I really think that that'll be fine. It's better to keep it superscript. I don't know why my brain just stopped working there for a moment. But anyway, so we're going to do that. And you're going to do the same thing. So like if you had 3 electron domains, you wouldn't need to use that 3rd p orbital. So it would just be sp2 hybridized. If you had 5 electron domains, you would use all of your p's, and now you also need to use a d. So it would be sp3d hybridized. Kind of get the trends that are happening there.
So then, like, what kind of questions would they ask?
Well, they could ask us a question that's just straight up, what's the hybridization? What I would see is they'd probably give you a compound, and then you kind of have to draw the Lewis structure in order to figure out what its hybridization is. But they could compare 2 different compounds and ask you to compare them based on their hybridization. Oh, that's what I was going to say before I covered up my circle.
A certain trend you can look at based on the periodic table for hybridization, or is it just based on whichever you do?
Yeah, it's not really, it's just going to be based on your domains. So I guess you could use your trends in terms of like how to draw your Lewis structures.
Yeah.
you know carbon's always going to have 4 bonds. So if you know it's a carbon compound, then it's probably going to be sp3. So there's tools you can use, but it's not really a trend. I was going to talk about sigma bonds versus pi bonds for a second.
Is it double bonds still with one electron?
In terms of,
Like in a loop structure.
yeah, if you were, right. So it's still going to be 1 electron domain. That is true.
I just wanted to check.
It's sigma single pies.
Right. But, right, that is where your question tricked me for a moment. What?
What's a triple?
And that would be 2 pi bonds, a triple bonds, 2 pi bonds, and a sigma bond. And so a sigma bond, you remember how I said the hydrogens kind of overlapped here? So that's a sigma bond. Bye, have a good night. So when we kind of overlap like that, that's what we call it a sigma bond. Whereas sometimes you can hybridize and have like 2 different bonds that kind of come side to side, and that's a pi bond. And so that only happens if you have a double bond or a triple bond. So sigma bonds, any single bonds, and then each additional bond is a pi bond. I got off track and confused. What do I need to say next to you?
Just keep it simple and say like a tron bond.
I don't know. Do you guys want to talk about Lewis structures?
I mean, yeah, I know how to draw them. It's just, it takes a little while. Are there any tips to like drawing them faster?
Well, do you remember the honk rule? Do you know that one?
I do.
Honk tells you how many bonds they're likely to make. And these are the 4 most commonly picked elements. Hydrogen's probably going to make 1. Oxygen's probably going to make 2. Nitrogen's probably going to make 3. Carbon's probably going to make 4. So when you're doing that, I mean, you could try to, let's say we had something like this. That's not really how it would be written. Let's just say it were like that, right? So if you kind of think about the one that you would start with is going to be the one that can make the most bonds. I don't even know. I just made that up. I don't know if that's a real thing. So you can put, and then like the order that it's written in is typically going to be the order that it goes. So when it's written like that, I would kind of connect all your compounds together. I'm going to go ahead and put a hydrogen in there. So my oxygen is going to make 2 bonds. That's done. Probably don't need to do anything else with that. Nitrogen is likely to make 3 bonds. So I'm going to put another hydrogen on there. And carbon's likely to make 4 bonds. So I need to put 3 more hydrogens on there. Jokes. Don't tell.
When you say that there's 2 central atoms again?
It can happen all the time. But most of the time, the way you would see it is like I would have my carbon like this and then my carbon like that. So you have your hydrogens kind of separated out like that. So I started to do that here. So this would probably have been written more like that. As I said, that's not probably a real compound. I just made it up. So internet world, don't yell at me. So that's a test taking tip. If we're trying to jump and have only so much time, we're just going to guess.
And usually the first one written in the compound isn't that usually the central atom?
Correct. Unless for some reason it's hydrogen and he's never going to be in the center. So then the angles, if you're going to memorize your angles, your geometry, starts in 162 on here. You do need to know all of these. And I would recommend that you kind of get to know them by their number of electron pairs, like just electron domains in general. And then try to say, okay, well, these are all the ones that have 3 electron domains. And kind of compare. That's going to be trigonal planar or trigonal pyramidal. And sorry, that's not going to be, that's a lie. Trigonal planar and bent. Right. Those would be the 2. And so then you have to then think next about, okay, so how many of those are lone pairs? You have to think. Oh, okay. So 162, and then it carries all the way to 165, which is a clue of how many there are. And this is a good chart because it also includes like an example of it, what it looks like, and then what that hybridization is. So this is a great chart to check out. Don't feel like you have to memorize the whole thing. Look for those patterns.
Did you say you're putting that one worksheet we got already?
Sure, I can put that one on Meadow too.
The chart thing.
Mhm.
It's somewhere in
Yeah,
here.
somewhere. Just
Yeah, no, I'm happy to print that for you guys. Do you want to talk about the trends?
Let me get a worksheet over that too.
I think you got a lot of worksheets over the trends.
Rows and whatnot.
Yeah, but knowing the trends isn't even half your battle. Like you are gonna have to explain them for sure. You need to say, and you have to use that words like minimize repulsions and understand. They are going to give you what? Coulombic attractions.
When in doubt,
Coulombic attractions. If you can figure out the subject is about, trends, it's probably going to need to use the words Coulombic attractions or repulsions or both in your answer. So make sure you use them appropriately. You can't just throw those words around and hope that they think that you know what you're talking about. But I think
a big statement and then like a one-line star
no, I don't think.
repulsions.
What I meant by all that was, yeah, no, that's probably not going to happen for you. So, okay, well, that's fine. I don't know.
Okay, well,
You guys want to call it a night?
yeah.
Okay, go home and study, and then I'll see you guys tomorrow. Bye, Internet World.